Today we're talking about lesson 4.3, which is solving systems of equations by elimination. We have already talked about solving systems by graphing. And graphing works well when equations are already in slope-intercept form. They're easy to graph, and they have integer points for their intercepts, where the two lines intersect. There's integer points. We've talked about substitution, and substitution works well when one variable is easily isolated, such as if one is already in slope-intercept form and then the other equation is not. When one variable is easily isolated, already isolated, or you can isolate it without creating fractions in the remaining expression. In that case, substitution works really well. But sometimes neither one of these is true, and in that case, you can use elimination, which we're going to talk about today. And just to clarify, all three of these methods can work anytime. You can always graph and get a solution. You can always use substitution and get a substitution. It's just choosing which one works best for the situation you're looking at. How perfectly do you want to graph these equations? How fine of a gradation do you want to make sure you can get that fractional intercept that's there? How careful can you be to carry fractions through multiple equations if you're practicing substitution? So it just depends on what method fits the situation. All three of them always work. There's no reason you couldn't use one. It's just choosing the best one for a given situation. So let's look at elimination. Before we get too far, I want to remember this truth we learned earlier in the year. If A equals A, which is kind of a silly statement, but A, does A plus B equal A plus B? And the answer, of course, is yes. That's a silly question. And we remember that this is the addition property of equality that tells us this. And in fact, we use the addition property of equality more often in this kind of a format. If A equals 7, A plus B equals 7 plus B. So I know that A equals 7. That's a much more interesting equation than A equals A. If I add 7 to both sides of that equation, is it still true? If I add B to both sides of that equation, is it still true? A plus B equals 7 plus B. And that is true. I think we know that, and we're very confident about that. And that is still the addition property of equality. Like I said, that's more often the way we actually see it written. But let's look at this one. If A equals 7 and B equals 3, does A plus B equal 7 plus 3? And we talked about this. I think if you think about it, it takes a little more thought, but it does, right? I have A equals 7. That piece of my expression is still here. And then I'm adding the same thing to both sides. I'm adding B here, but B is exactly the same thing as 3. So I'm still adding the same thing to both sides of the equation. This is still actually the addition property of equality. And then the last one, what if I had 3A plus 3B? Does that equal 21 plus 9? And it is still true. It's just now I'm not using just the addition property of equality, and I'll let you think about this. If you have more questions, you can always ask. This one is not just the addition property of equality, where I'm adding something to both sides, but it's also the multiplication property of equality. I have to use both of these to get this final expression. So let's go ahead and look at some examples of what solving by elimination might look like. Here are two equations that I want to look at solving by elimination. I could certainly solve these by graphing or by substitution, but let's look at what it would be like if I solve these by elimination. To do that, I notice that I have a plus y and a minus y. They both have a coefficient of 1. So they have the same coefficient. I can add these two equations to each other. And I would get, if I add the x terms, I get 3x. But if I add plus y and minus y, those terms go away. I've eliminated them from my equation. 7 plus 2 equals 9. And now I have an equation that only has one variable in it, and I can determine that x equals 3. Using that value, I can come back up here where x plus y equaled 7. So 3 plus y equals 7, and y equals 4. I was able to determine the value of x by eliminating it. Right? I'm using this addition property of equality. I was able to eliminate this term, solve for the remaining variable, and then substitute back to get a final solution. So here is another example. 2x minus 4y equals 2, and negative x plus 4y equals 3. Again, if I look, I see that the y has a common coefficient. They're both 4, and they have opposite signs. So if I add the two equations, 2x plus negative x leaves me with x. These two have opposite signs. They're going to cancel. 2 plus 3 equals 5. So I solve for my x value. Then I'm going to go back. I can choose either equation. I'm going to go ahead and choose this bottom one. Negative x plus 4y equals 3. Opposite of 5 plus 4y equals 3. 4y equals 8, and y equals 2. So my final solution would be 5, 2. So in both those cases, I noticed that I had a common coefficient. By adding the equation, I eliminated that term and was able to solve for the remaining variable. Of course, sometimes it's not quite that easy. There are a couple of other possibilities. Here, I have 3x plus y equals 7, and x plus y equals 5. If I look, I see that I still have a common variable. I still have a common coefficient, 1 and 1. But if I were to add these, I would get 4x plus 2y equals 12. And this does me no good. I have not eliminated anything. So I'm going to go ahead and take that out and say, what happens if we subtract? Remembering that if I'm subtracting this equation, I have to distribute the minus sign to every single term. 3x minus x is 2x, y minus y. Now those are eliminated. 7 minus 5 is 2. I've eliminated a term, and x equals 1. I could go back and solve. X plus y equals 5. 1 plus y equals 5. Y equals 4 for a final solution of 1, 4. So if the signs are the same, like you see here, plus y, then you subtract the equations. When the signs are opposite, like you saw here, minus 4y plus 4y, then you would go ahead and add the equations. But there is actually still one other case that we have. Sometimes you might have something like x plus 3y equals 7, and 2x plus 2y equals 6. So here, I don't even have any common coefficients, right? Let's see if I can get another color pen. Sometimes it works. It's not working today. Okay. I don't even have any common coefficients. So what I'm going to do is I'm going to take this entire equation and multiply it by 2. Right? Here I have a 2 and here I have a 1. If I multiply that entire equation, I get 2x plus 6y equals 14. This one I'm just going to copy across. 2x plus 2y equals 6. By multiplying, I have now created a common coefficient. So now if I subtract both sides, these terms go away. Minus 2y leaves me with 4y. 14 minus 6 leaves me with 8. And y equals 2. I can go back and substitute. 6 plus 3 times 2 equals 7. X plus 6 equals 7. So x equals 1. And my solution is 1, 2. So this is where you would use multiple properties of equality, right? First, I multiply to create a common coefficient. Then I go forward with the elimination process to find a final solution. So here is what that elimination process is. Solving by elimination, you identify a variable that can be eliminated. If neither variable has a common coefficient, find the least common multiple. So in that last example, I had a 1 and a 2. Here's a 1 and a 2. So the least common multiple is 2, so I created that 2 by multiplying. Okay? So if neither variable has a common coefficient, find the least common multiple and rewrite equivalent equations. Sometimes you have to multiply both equations. Add or subtract equations to eliminate one variable. Remember, you add if the coefficients have opposite signs, you subtract if they have the same sign. Then you solve for the remaining variable and substitute into an original equation to find the other variable. Don't substitute into one that you've modified. Always go back to the first ones just to make sure you're using the right equation. So those are the steps to do solving by elimination. Let's see if we can look at one more example. I want to look at this one. If I look, I have 3 and 4. Oh, those are not a common coefficient. The closest I can get, the LCM, would be 12. Here I have 2 and 3, and their least common multiple would be 6. Just in general, I like to use the smaller numbers just because it makes easier multiplication later. So I'm going to go ahead and go with this 6, least common multiple for y. So I'm going to multiply my top equation by 3. I'll get 9x plus 6y equals 3. I'm going to rewrite this bottom equation multiplying by 2, and I will get 8x plus 6y equals negative 4. Now that I've rewritten those equations, I can go ahead with the process. These 6's have the same sign, so I am going to subtract. 9x minus 8x leaves me with x. These are going to go away. 3 minus a negative 4, it changes the sign of the 4, and I have 7. So x equals 7 is one of my points. Then I have 3x plus 2y equals 1. Back to an original equation. 3 times 7 plus 2y equals 1. 21 plus 2y equals 1. So 2y equals negative 20, or y equals negative 10. And my solution is 7 comma negative 10. So just an example that sometimes you do have to multiply both equations to get a solution. Here is the concept summary, just an example of more specifically when you would solve by substitution or when you would solve by elimination. And I'm going to go back one more time and let you stop right here. Again, the process of solving by elimination, first you have to identify the variable that can be eliminated. Sometimes they'll have the same coefficient right away, or you can identify the least common multiple and rewrite them to have equivalent equations so that they have a common coefficient. After you've done that, you add or subtract to eliminate one variable, solve for the remaining variable, and then substitute back into the original equation to get the value for your last variable. And just a last point, your solution will always be an ordered pair, right? It will always be two numbers, right? We have equivalent equations. It'll always be an ordered pair, x, y.